Hello, everyone. I'm Ashiqur Rahman from the University of Arizona, and today I'll be presenting on data-centric forwarding in mobile ad hoc networks, baseline design and simulation analysis. Let's jump in. Packet forwarding in MANETs is inherently challenging. One reason is packet collision at the receiver. Another is channel contention when multiple sender-receiver pairs exchange data at the same time, but overlap transmission range. Furthermore, mobility leads to frequent path breakage, making communication even more difficult. And IP-based MANET routing protocols face some challenges. Most protocols follow a two-step process, establishing an end-to-end path and then exchange data. In this example, the requester broadcasts protocol packet to learn a path towards the data node with another protocol packet. The requester then unicasts a request packet to get a data packet back. Thus, on packet loss, these steps repeat, gradually becoming costly for data exchange. On the other hand, named data networking, or NDN, is an emerging data-centric architecture that offers potential advantages over IP routing in MANETs. Here, interest or request packets and data packets carry names instead of IP addresses. Thus, a consumer can learn a next hop towards any data node with interest packets directly without needing a separate control plane. Naming also enables caching, where a middle node can serve data from cache. It also provides default multicast, where one data can serve multiple consumers, and loop detection is also built in. However, these features are absent from default IP-based routing. Moreover, even flooding works to some extent, whereas data flooding in IP does not work without routing protocols such as AODV. So we've seen the challenges of IP-based MANET routing, and in theory, NDN should be a better fit for MANETs. However, existing works lack the analysis of a key question. Can NDN be a better fit than IP in MANETs? To answer this question in this work, we perform a baseline comparison analysis between the two architectures out of many available designs. Therefore, the difference in performance comes from the difference between the architectures and not only the routing. For this comparison, we chose a broadcast-based learning as their routing basis and a request-response application where one request packet retrieves one data packet. Please refer to the paper for more details on application setup. Thus, we use the AODV routing protocol as an IP baseline for its well-known design. However, NDN's broadcast-based self-learning is only tested on wired local area networks, and we will show that it struggles in MANET. Next, we show that a minimal but appropriate changes to the existing NDN forwarder can offer better mobility support, which we call the data-centric ad hoc forwarding, or DAF, as the new NDN baseline. The key takeaways of this work are as follows. We show that our baseline DAF overcomes the limitations of flooding and self-learning. We analyze the overhead of IP-based AODV routing. Finally, we show that an NDN-based baseline forwarding strategy outperforms IP-based baseline routing in different communication scenarios. Let's start with the first one. An NDN-based flooding suffers from very high collision and contention from broadcast storm. However, caching and multicast offers better retrievability under mobility and when the network is sparse. So even if path to one data node fails, another may bring the data back. Next, NDN self-learning strategy for local area networks struggles under mobility. Only a consumer initiates broadcast interest or discovery to learn a next hop on the shortest path and switches to unicast. This unicast phase continues until an application timeout, even if packet loss occurs in between. This leads to delayed discovery feedback, and many unicast interests are wasted. Self-learning also suffers from negative acknowledgement, or NAC overhead. A node sends a NAC back to the consumer when it has no next hop neighbor towards a data node. This not only increases network traffic, but also prematurely removes valid next hop entries in the network. Moreover, a consumer does not know who generated the NAC. Our proposed Indian-based DAF brings a balance between flooding and self-learning. DAF significantly reduces network traffic of flooding, and any node can fall back to discovery, unlike in self-learning. DAF does so by using in-network RTT measurement to expire the FIB entries of potential unreachable next hops. This is similar to TCP RTO calculation, but is decentralized and helps to avoid NACs as well. Please refer to the paper for more details. The trade-off is that DAF may form suboptimal paths, but it can react faster to packet loss and mobility. In the example, when XD link breaks, X can forward interest as broadcast to learn a new next hop Y towards the data node. We also introduce further DAF improvements only by manipulating the existing Indian forwarding tables and pipelines. The first one is DAF achieves multicast through broadcast. For example, when X has 2 PIT entries from an aggregated interest, it broadcasts the data received from D. And this design helps to reduce the network traffic in certain cases. Next, DAF accepts unsolicited broadcast data, which enables opportunistic caching and FIB updates. And this offers better retrievability on interest retransmission. With these managed specific improvements in mind, let's look at some simulation results comparing DAF, flooding, and self-learning in India. We use Indian SIM for the simulations. Each node has single NIC and communicates with other nodes over a single channel. Further details are available on the paper. And again, the purpose is to analyze the baseline architectural performance. We start with the results from one-to-one communication, where each consumer peer exchanges unique name prefix. NF represents flooding and SL represents self-learning. The x-axis on both plots show different moving speeds of nodes. The y-axis on the left plot shows the data retrieval success rate, and on the right plot, we have the network transmission events per data packet received. Note that neither of them have any separate protocol message overhead. The lower success rate of flooding results from very high transmission overhead, but does get better than self-learning under mobility with caching. Although self-learning performs well and when nodes are stationary, it suffers under mobility for its shortest path priority design. DAF balances these two with an average of 42% and 178% more success rate than flooding and self-learning, respectively. Next, we show a quick analysis of Indian's caching effect under mobility. Here, we also include many-to-one communication where multiple consumers ask for the same data from the same producer. Caching helps flooding the most with the highest success rate gain and significantly reduces transmission overhead as interest forwarding gets lowered. Recall that flooding in IP does not work without routing protocols. Next, caching effect on self-learning and DAF is very low as they both try to learn a single next hop towards data. Self-learning shows very low transmitted bytes per data as most interest packets are lost. With DAF's balancing performance, the next sections will only include DAF for Indian performance analysis. Next, we show the analysis of AODV's routing overhead in manets and compare it against DAF. AODV routing has two distinct overheads, one from protocol message exchange, which is used for route setup and maintenance. Moreover, request or data packets are only forwarded over a valid path, and finding and maintaining a valid path incurs added delay. Thus, total latency becomes the summation of route setup, maintenance, and data exchange. And this added latency degrades the application performance under mobility. Now, let's analyze how these overheads affect AODV's performance. or IA in short, under mobility comparing against DAF. We see that latency and protocol overhead of AODV increases with speed, and together they yield lower success rate compared to DAF. On average, DAF achieves 38% more success rate as its latency is 75% lower with no protocol overhead compared to AODV. DAF does yield a slightly larger hop count due to its suboptimal paths. Please refer to paper for more details with verification results. We then further analyze how an Indian-based Indian baseline can outperform IP baseline under different communication setup. To do so, we perform further evaluation, which involves effect of network size or number of nodes. This presents the worst case for NDN forwarding, as caching and multicast effect is almost non-existent. The many-to-many communication considers multiple consumers asking for same data from multiple producers. It portrays the best case for NDN primarily with the help of caching and distributed network load among multiple data nodes. Next, the many-to-one communication primarily shows NDN's aggregation effect, which reduces producer load. Here, the x-axis and the figures show number of nodes and application retransmission count as a tuple. The success rate improvement with application retransmission for both AODV and DAF is trivial. However, AODV's success rate goes down with increasing network size, as it also increases the protocol overhead in the network. Note that DAF's average hop count is higher, which is from its opportunistic, suboptimal, and faster path recovery mechanism. We consider it a fair trade-off for achieving an average of 45% more success rate than AODV. Next, in many-to-many communication, DAF achieves an average of 83% more success rate than AODV. Effect of NDN's caching, multicast, and DAF's closest data node selection is verified with 80% lower transmission events and 58% lower average hop counts than AODV. Note that AODV still maintains the one-to-one communication performance, as the underlying IP architecture lacks caching and multicast by default. Finally, in many-to-one communication, further evidence of NDN caching and multicast is visible. They help to reduce the network load at and near a producer node. Caching helps to lower the hop count of DAF by 27%, while caching and multicast together help to lower transmission events by 42%. However, in AODV, one data node maintains multiple dedicated flows with multiple consumers, which increases the transmission overhead, causing more loss from collision and contention, and thus increases protocol messages for path recovery. As a result, the success rate of DAF is 50% more than AODV. To conclude, we have shown that DAF properly adapts the Indian architecture in manets with minimal changes. It also significantly lowers the latency by avoiding protocol messages and using Indian's interest data packets for learning. Finally, the Indian-based DAF significantly lowers the network overhead in cases where multiple consumers ask for the same data. Its software-based in-network calculation and packet forwarding is hardware independent. Thus, we verify that Indian is better fitted for manets, and future research can offer further improvements on top of our baseline. And thank you for attending the talk.